So we did Cauchy's integral formula in previous lecture, and what it says that if you have an analytic function fz, it is analytic on some contour and with inside of that contour, then we'll see the simple closed contour. And if you take any point within inside this contour C, then the value of the function at that point is given by this integral representation 1 over 2 pi I integral over C f of theta over theta minus z dc of theta. This is Cauchy's integral formula that the value of the function inside the contour is completely determined by the by the values of the function on the contour. Whenever function is analytic within and on the contour C. So now we will prove a much stronger result, and from within that result we will get a Cauchy integral formula for derivatives. And the result that we will prove today is that if let f be an analytic function on a domain D, then the derivatives of f of all orders exist on D and are analytic in D, are analytic in D. This is a very powerful statement. Now it states that that means if you have a function analytic, f function is analytic on D, then it says that that is, if f is analytic on D, then it says that all the derivatives of all orders of f exist on D, and they are there. It is not that the derivatives exist. The function that you obtained after differentiating this capital F, all those functions are also analytic. They are also analytic. That means derivatives of analytic function are also analytic. So this theorem here proves that initially up to this point I used to repeat this one statement that sometime indeed I have used it only once in proving the partial converse of Cauchy theorem, that analytic function has continuous partial derivatives. But now once you have this result, it doesn't use that continuity part of the derivative of a function. It only says that f is analytic. It's just differentiable in a domain D, it's analytic, then implies that its first derivative is analytic. If its first derivative is analytic, that is continuous. And if that is continuous, that means the partial derivatives of f will be continuous. So this contains everything, and it doesn't say that only the first derivative. Every partial derivatives of all possible orders of the real and imaginary part of f are going to be now continuous and differentiable. And let us prove this. And Cauchy integral formula is very instrumental in proving this result here. So what we are going to choose, we are going to choose an arbitrary point in domain D. That we have this domain D, and we are going to choose an arbitrary point here, Z0, and let me write it Z0. And since this is a domain, I can find a disk of certain radius which lies inside this, and let this disk be of some radius r. And then note that disk is a simply connected domain. So if I choose any other contour, let me choose any simple contour inside this disk C. So the first thing that I'm going to do here is to show that the derivative of a function, first thing, first thing uh, we are going to establish is that derivative of this function f at z naught has also an integral representation. It is given by 2 upon, it is 1, it's actually 1 upon 2 pi I integral over this contour C. Indeed, this is not true. This you don't need only this contour C. It can be any simple closed contour. But here I am taking this particular contour. Now, this is even not particular. This is the contour within this disk. But this will be true for every whatever simple contour you take. This formula will always hold. Zeta minus z naught square dz. First, we are going to prove this, and then we will prove that this function, the derivative of f, is differentiable, and then we shall show that derivative of f is differentiable at z naught. And z naught is, we are taking z naught to be an arbitrary point in domain D, and in this way it will be differentiable at each point of domain D, and hence it will be a analytic function. This is the definition of an analytic function in domain D. So let us look at this thing. Now again, choose H non-zero H such that z naught plus H lies within this, is inside the interior of this contour. See, this is always possible to choose because it is an open set and you can always find, and if it doesn't lie in a contour, you can take contour to be the boundary of this disk. That will also work. So you can always choose H to be small enough so that Z plus H is still inside this contour T. Then by Cauchy integral formula, look at this expression f at z naught plus h minus f at z naught upon h. You just first apply the Cauchy integral formula. We have, okay, it is the same thing. It is 1 upon h. You keep it outside, and then you have f z naught plus h by Cauchy integral formula. It has to be 1 over 2 pi I integral of contour C. It has to be f of theta, theta minus, it has to be z naught plus h, but minus bracket hata dunga, it will be z naught minus h d theta minus f of z naught by Cauchy integral formula. It will be 1 over 2 pi I, and integral over C, it is f of theta upon zeta minus z naught d zeta. So this is the expression. You simplify it. You take out 1 upon 2 pi outside, and you just simplify. You take the what you get after simplification is this thing. You can take 1 over 2 pi I, 1 upon h outside. Integral you can take common because of linearity property of the integral. It is C f of theta. Then you have 1 over theta minus z naught minus h minus 1 over theta minus z naught. This is this. 1 upon 2 pi I, 1 upon h, integral over C, f of zeta What are you going to get if you take the LCM? LCM will be zeta minus z naught minus h into zeta minus z naught, and then you cross multiply zeta minus z naught, and zeta minus z naught will be cancelled. You will have plus h, and you keep this h here, and it is t zeta. Now you can cancel out this h. It is a non-zero quantity, and it's in denominator also. So you can cancel this. You will not have this, and this implies that now what you have left, you have this thing f z naught plus h minus f of z naught upon h. This quotient is equal to 1 upon 2 pi I. If this quotient has integral representation, f theta upon theta minus z naught minus h into zeta minus z naught d zeta. Okay. Now, as per our assertion in the beginning, we want to show the integral form of the derivative of the function. For that, to evaluate the derivative, I need to take the limit h goes to 0, and for that I need to show that this limit h goes to 0, 1 upon 2 pi I c f of theta upon zeta minus z naught minus h multiply zeta minus z naught d zeta is equal to 1 over 2 pi I integral. I mean, why do we need to write pi? It is understood pi is there. Pi will not be affected with uh, z. It has no role with z. Let's remove this. We just need these integrals to converge. I need only this to be equal to f of theta zeta minus z naught square. I need this to be equal to when h goes to 0. And if you are able to establish this thing, your right hand side in this equation star will be replaced by this integral, and left hand side you will have the derivative of the function at z naught, and that will prove your first assertion. So first let us look at the modulus of the difference of these two integrals. So what is the modulus of the difference of these integrals? Consider this modulus. This is integral over c f of zeta zeta minus z naught minus h naught into it is zeta minus z naught d zeta minus integral over c f of zeta over zeta minus z naught square d zeta. You simplify it, it is equal to integral over zeta f of zeta into what you are going to get here. The LCM will be, the LCM is going to be zeta minus z naught and minus h naught into zeta minus z naught square, and in the numerator you will have zeta zeta minus z naught minus zeta minus z naught minus h naught. And if you simplify this numerator there, what you are going to have, you will be left only with, because this zeta and okay, I just erased it. I just need to change the color. See here, this zeta and zeta will cancel out, z naught and z naught will cancel out, minus and minus will be h. This is h, not h, h. So you are left with h. So you have this thing, and at the same time I'm taking modulus inside this integral. It will be less than or equal to mod of h. H has nothing to do. You can bring it out of the integral. It is our c contour mod of f zeta mod of t zeta. Our denominator you have zeta minus z naught minus h naught upon zeta minus z naught square. And so let's look at this. I want this thing go to 0 as h goes to 0. This is what I want to show as h goes to 0. This is what desired. This is what we want to show. But let us check. Let us check what is going to do. See first. To C is a contour, and contour is always a compact set. You have f in an analytic function. Analytic function is always continuous, and you know that continuous functions and compact sets have their maximum. So let us take m to be the maximum value of mod of f of zeta over this contour C. This always exists, and further you have this situation. You have this contour. I'm just drawing now contour C, and you have z naught inside this contour, and zetas are coming from the boundary of this contour. What you're going to do, you just measure the distance, the minimum distance of points of this contour from z naught, and let that minimum distance be d. And that means what is d? D is the distance of z naught from C. And obviously this distance is positive because distance, why it is positive? Because z naught doesn't lie on the contour. The distance is 0 when the point lies on the set. So far it is a point of a completion. It's out. So then that means if d is the distance, this is by definition is the minimum distance of z naught from the points of this contour C. This implies that this distance is minimum from zeta minus z naught for every zeta in contour C. You have this inequality. And if you have this inequality, then that means that implies the reciprocal of this 1 upon mod of zeta minus z naught has to be less than 1 upon d, and square of it will be less than d square. Also, I have another term in the denominator, and what is that denominator? We have this zeta minus z naught minus h naught, and see let's how it can be tackled. I'm going to make the use of triangle inequality. This is zeta minus z naught minus h naught. This is h. This is not h naught. This is h only. So this is h. But first note that we can choose h to be arbitrarily small. So what I'm going to choose, I'm going to choose h such that modulus of h is much lesser than the distance of d that I just defined here. Now I can write it to be greater than, less than or equal to. No, I need to be greater than or equal to mod of zeta minus z naught minus mod of h. This is the part of the triangle inequality. Indeed, it is modulus of these terms, but since this is further greater than zeta minus z naught, this modulus is greater than d, and this is mod of h. So I can remove this outer modulus because of my this assumption here that mod of h is less than d. And then this implies what is the reciprocal relation? For reciprocal, I have zeta minus z naught minus h is less than or equal to 1 upon d minus mod h. So I have all these inequalities here. Now I will substitute these inequalities in this integral. What I can have now, therefore, I have this thing integral over c. It is mod of h. It is mod of f of zeta upon zeta minus z naught minus h modulus into modulus of zeta minus z naught square mod of d zeta. So I have modulus of fz because I have chosen its maximum, so it has to be less than or equal to mod of h, and the mod of fz zeta will be less than its maximum. And in denominator, you see these reciprocals. This modulus of z minus z naught minus h was less than t minus mod h, and mod of zeta minus z naught square is less than, reciprocal of it is less than d square, and then you are left only with integral over c mod of d zeta, and what is left with is nothing but the length of the arc c, and let that length be L. Let us this let me call this length. Let it be, let this be L. That means you have this inequality less than or equal to mod h times m L upon d minus mod h into d square. And now you take the limit h goes to 0. Denominator will not affect because it is d minus mod h, and you have your selection is like mod of h is much less than d, so that d minus mod h is always going to be at least at most, not at most, it's always going to be positive part, because mod of h is never going to be equal to d. So denominator part will approach to d cube, and numerator will go to 0, and hence the total limit will go to 0 as h goes to 0. And this is the requirement, this was the requirement, that this limit must go to 0 as h goes to 0. Hence we have this thing that limit h goes to 0, f of z naught plus h minus f of z naught upon h. I just proved it to be equal to 1 over 2 pi I integral over contour c. Note that c can be any contour. The only thing that this contour must enclose z naught. Simple closed contour must enclose z naught. F of theta upon zeta minus z naught square d. But what is the limit of the left hand side? Since you have f is analytic function, and this limit, that means f is differentiable, and this limit is nothing but the derivative of the function at z naught. This is derivative of the function at z naught. This is equal to 1 upon 2 pi I integral over c f of theta over zeta minus z naught square. So without, still we haven't proved that this derivative is a differentiable function, but the major thing that we have proved here now is that integral of analytic function also has a not integral, derivative of an analytic function also has a integral representation given by Cauchy integral formula. Note that the difference here is in denominator the power is 2 now. The first derivative, the power is 2. It is plus 1 of the order of the derivative. And now let us proceed to prove that this is actually differentiable. Now, what are we are going to do? We are going to apply the same kind of argument, applying the same procedure to f prime in place of f. We get, हमें क्या मिलेगा? Look at this thing. What you will get derivative of f prime z naught plus h minus f prime at z naught upon h. If you compute this, you have expression, you will have 1 upon h into 1 upon 2 pi I. You are just using this integral representation, and it is equal to integral over c. It is f of theta. And now let me write it smaller. Oh, I just need eraser. So it is f of zeta d zeta into upon, not upon, still I'm just messing up it. So you will have, I have to have a space to write this thing. I will have, okay, no, I just need to write in a bigger space. Let me remove this. This is equal to 1 upon 2 pi I into 1 upon h, also integral over c, and 1 upon the integral representation. In the integral representation of f prime z naught plus h, you will have zeta minus z naught minus h square minus 1 upon, if you will have zeta minus z naught square, and then it will be multiplied with f of zeta d zeta. So again you are getting the same kind of uh, mm, method, same kind of track that we encountered while doing the integral formula for the derivative of the function, analytic function f. And now what you will have again this, if you simplify this thing here, you will have, mm, let us simplify this inside out first. You will have zeta minus z naught square. So it is zeta minus z naught square minus, and zeta minus z naught square minus h whole square. So you just first take its expansion, zeta minus z naught square. You will have zeta minus z naught square plus h square, but being multiplied by minus from outside, it will be minus h square, and then it will be minus 2 times, but minus being out again multiplied with minus from outside, it will be plus twice h times zeta minus z naught. And you will have in denominator, you will have zeta minus z naught minus h square into, it is zeta minus z naught square. So you will have so many things cancelling each other, not so many, but few terms are cancelling, like this and this term will cancel out, and then you have h in denominator here. This h and this square will cancel each other, and h of this term will be cancelled out. So also, I don't think we will be left with anything else. Okay, then you have this zeta minus z naught also being cancelled out with the this square of this term here. So what you are left with, I'm going to write it here, and this expression I'm left with minus, I'm left with 2 minus h. Is it correct that is this the correct? Can somebody tell me if I haven't done any mistake here? Can you check it? No, but then okay. The thing that I can cancel out the h, but I cannot cancel out zeta minus z naught. So because
Yes,
h
sir.
is always present there. Okay, yeah. This is what I was.
वो कॉमन नहीं आएगा ना?
हाँ, ये common नहीं आएगा ये.
Yes, sir.
So the expression is, now you have 2 times zeta minus z naught minus h upon, you have this zeta minus z naught minus h square into zeta minus z naught square. And then again, so let me write this integral completely, so that I'm writing this integral here only. so that I don't have to get to somewhere else. I'm writing it inside this bracket. So you have 2 times zeta minus z naught minus h upon zeta minus z naught minus h square and theta minus z naught square. Again, as in the previous case, what you will have to show, you again, since f being continuous, it will be less than or equal to it will be less than or equal to something, some term, but still not exactly this thing. Okay, okay. Now you have to show that this quotient is actually equal to, let me denote this quotient by delta prime f at z naught, just a notation. Then we have to show that this it has an integral representation f z prime. I want it to be equal to 1 upon 2 pi I. I want it to be 2 upon 2 pi I. Indeed, I will write it at 2 as a 2 factorial. Integral over c, it has to be f of zeta upon zeta minus z naught square d zeta. I want this thing to go to 0, so that will imply, as h goes to 0, then this will imply that the limit of this quotient exists. This limit exists and this limit is equal to this value of this integral formula. And if you substitute, you have computed this value here. If you substitute those values here, you will get some expression here. You will have this integral 1 upon 2 pi I modulus, and you have integral over c, and you have lost the h. Now you have 2 times zeta minus z naught minus h, and in denominator you have zeta minus z naught minus h square and zeta minus z naught square, and the LCM will be this LCM will be zeta minus z naught minus h whole square into zeta minus z naught square. So if it has to be the LCM, what I should multiply with this minus part, because here I have 2 also. I have taken only outside. I have taken, yeah, I can take outside the 2 also. I can take outside 2 also from here, so that I can remove this 2 from here. I do not require this 2 here. So then 2 being taken outside, and then I will be having this, I have to multiply this zeta minus z naught square in denominator with zeta minus z naught minus h whole square. So that I will have zeta minus z naught minus h whole square, and then it will be multiplied with f zeta and d zeta, and that will be some modulus. And then what I want to tell you about, because I don't need to calculate this thing because it follows the same procedure, then this part, this integral will go to 0. Same way you have to, you will get all the estimates that we found here, that zeta minus z naught h will be its reciprocal will be less than d minus mod h, and zeta minus z naught square will be its reciprocal will be less than 1 upon d square, where d you will choose the distance of the z naught from the points of the contour C, and f being analytic and it is continuous, it will be you can replace it by its maximum, and this term will go to 0 as h goes to 0. And what will it establish? It will establish that the limit of this encircled coefficient exists, and this value of this limit will be equal to limit h goes to 0, f at z naught plus h, the derivative of f at z naught plus h minus derivative of f at z naught upon h is equal to 2 factorial upon 2 pi I. It is integral over c. It is f of zeta upon zeta minus z naught. Here you will have now power 3. It will be cube. So what I did, I just wrote a wrong thing here. It has to be cube here, so that then things become and normal, so that I have to multiply here numerator also with zeta minus z naught also, so that this is a part of simplifications. You can do it on your notebook. It will be d zeta. And the left hand side, when this limit exists, you say that this is the double derivative of f at z naught exists, and the value of this double derivative is given by 2 factorial upon 2 pi I integral over c f of zeta zeta minus z naught cube d zeta. So what it implies now, finally, it implies that the double derivative of f exists at z naught, and you had chosen z naught to be an arbitrary point in domain D. That means this double derivative of f exists at each z in D. And you remember a function which is differentiable at each point of a domain D, that function becomes an analytic. The derivative of a function becomes the function becomes analytic. So double derivative is a derivative of the derivative of f. That means f derivative of f is analytic. This is analytic on D. And similarly, applying this same argument, to derivative of f in place of f, what we get? We get that double derivative of f is analytic, and so on. You will get third derivative of f analytic, you get all the derivatives of f to be analytic functions. Is it okay?
Yes, sir.
So in this way, this is a major result where you prove that the derivatives of analytic function are analytic functions. And this theorem doesn't establish only the derivatives are analytic. It establishes that if the function is analytic, what is the definition of analytic? You just assume that this function is differentiable on a domain. Then that simple thing implies that this function is double differentiable, 3 times differentiable, and indeed all other derivatives of exist, and all the derivatives are analytic functions. So this is a big major achievement of this analytic function theory. Another thing that I want to note down here, the process that we followed in proving this theorem is we had to prove that the derivative of an analytic function is analytic. But to prove that, we proved a certain thing, that if you have function f which is analytic in a contour C, it is analytic in a contour C, and within contour and on the contour C, then it says that its all derivatives are analytic, and for any point inside this contour, you have the expression of this derivative given by, because you got the expression for double derivative. You had this expression for double derivative to be 2 factorial upon, you had this 2 pi I upon integral over c f of zeta upon zeta minus z naught. It is zeta minus, sorry, not z, it's only z cube d zeta. And then you will proceed by induction, and you will be able to establish that this nth derivative of f at z is given by n factorial upon 2 pi I integral over c f of zeta. See, f is not changing; it's remaining the f only. You do not require any derivative of function to calculate the derivative of any order derivative of the function. You just need the information about f, and where the order reflects in the integral, it reflects as a power in the denominator. It is plus 1 and plus 1 d zeta. This is the Cauchy integral formula, and it can be established very easily through using induction process, because you have done it for the first derivative and second derivative. You have proved it, and you just assume for nth derivative, you just assume it nth derivative and you prove it for n plus 1th derivative. It's not a big thing that you assume that it holds for, then you just apply the same process to nth derivative, you get this information. So this is another expression. This is more general Cauchy integral formula, because if you substitute n equals to n equal to 0, so according to the convention of notation, zeroth derivative of a function means the function itself. Then this encircled formula reduces to the usual Cauchy integral formula. And you have to remember this one also. This is very important. And another remark that you need to observe is you have Cauchy-Gorsa theorem for multiply connected domains. The proof that we did here, in each of the proof we considered simple closed contour, and we considered function to be analytic inside those contours also. And what is the inside of a simple closed contour is a simple connected region. And but what if you have multiply connected regions? You have a whole type, you have these regions, then you apply the Cauchy integral theorem, Cauchy-Gorsa theorem for multiply connected domains instead of Cauchy theorem, improving the Cauchy theorem for simply connected domains. Because we what we did, we used you take any point here. If you want to prove the Cauchy integral formula, you take any point here. Because interior of these circles, these smaller contours is not part of our domain. Then I have to prove the Cauchy integral formula. But here, what I'm going to take, I'm not going to take it to be a contour, because it's not a contour now. It is a piece. You have three pieces of contours here. So I can call it to be a D, be a multiply connected domain, multiply connected domain. You remember the simplest way to identify multiply connected domain when it has holes in it. How many holes? That hardly concerns, but it must have at least one hole domain. And what is the boundary? Look at the boundary. Boundary of this is consists of
Yes, sir.
so
So,
sorry, the screen went out. So let me write again. You have multiply connected domains, and you have D is multiply connected domain, multiply connected domain. And what is its boundary? Look at its boundary consists of these three pieces. Its boundary consists of these three pieces. One, you have this contour, and you have this bigger one, and each piece is a contour. But you cannot say that boundary is a contour. But what you can say, what is a contour? Contour is a piecewise smooth curve. So you can say that boundary is piecewise smooth. And also I need to take D to be a bounded multiply connected domain. I cannot take it to be unbounded. It is a bounded. It is a bounded. Let us keep it also bounded. Piecewise smooth, and delta D be piecewise smooth. And if now it says that F is analytic, if F is analytic in D, and on boundary of D also, then for any Z in D, you have the nth derivative of this function at Z given by this formula n factorial upon 2 pi I integral over the boundary of D. It is f of zeta minus z power n plus 1 d zeta. And for proof, you don't need anything special, because you to prove the Cauchy theorem, what you require, you just require the Cauchy-Gorsa theorem, and you can apply Cauchy-Gorsa theorem here also. and everything will proceed accordingly. You will not have any trouble. So this is what we stop here for Cauchy integral formula. And if you have any questions, you can ask. बोलिए जी.